Well, I think it's time to start. So, hello everyone, and thanks you all for coming, because it's quite a good turnout and full house, in fact, and more on Zoom. So thanks a lot. And for those in the room, I have to say a bit of housekeeping about we're not expecting a fire drill. So if the alarms do go, we basically file out the way we came in, turn right out of the building. We're not allowed to cross the road, apparently. And then we will gather at Chapel Row on the green space there and check that we'll have to check names and check nobody's left in the building. That's never happened, but there's always a first time. My name is Paul Jackson, and I've been asked to convene this series of talks about Bath heritage. And this is the first one, so it's great to have such a good turnout. Thanks again for coming. You might have seen on the screen that the next talk is on the 23rd of May, 22nd of March. And they're going to, Wednesday the 22nd of March, let's just get that right. And there are 6 talks, each one dedicated to one of the reasons that Bath has been given the accreditation as a World Heritage Site. So they'll go on from the 22nd of March to the 3rd of May. Now, one of the aims of the Heritage Series is to show how the past marries with the present and how the present can gain from the past. So tonight's talk is really pleased that we have Thomas Kjeldsen here, who's one of the projects he led was to apply mathematical modelling to Bath's historic flood data to provide a basis to assess the risk of future floods. Thomas is a senior lecturer in the Department of Architecture and Civil Engineering at the University of Bath. His research areas include the impact of climate change and the changes of land use on water resource systems. And one of his current research topics is flash floods. So, Thomas, it's all about floods tonight. I need to hand over to you.
Thank you, Paul. Thank you for the introduction. Thank you very much for the invitation to come and talk, and thank you to everybody for turning up. So the title is Bath Floods. I think that was Paul's idea. So I gave it a subtitle calling Researching the Past to Understand the Future. So this is research that we've undertaken at the University of Bath. So we are civil engineers, so we're sort of trying to quantify flood risk for the purpose of designing stuff for infrastructure and for supporting spatial planning, where we should build and where we shouldn't build. So it's in that context that we have researched historical floods. So we try to dig out evidence of floods from as far back as we can to try to help us understand the current flood risk, the risk we're currently facing, and also as a benchmark for what we might come to experience in the future. I would like to also thank my long-term collaborator, Joanna, who started her professional life as an undergraduate at our department, rose to the ranks and is now a lecturer at the Greenwich University, who has made a very big contribution to this. So thank you very much, Joanna. So I'll see if I can move these forward. No. That's not it. Is there some technical help at hand? Oh, there you go. You just have to click enough. So this is the main topic of tonight is the River Avon, the river that runs through the city of Bath. So it starts up here somewhere. So we're starting up here near Bathford, where the railway line crosses over the river. That's a key point. Haultney Bridge will feature a few times. Halfpenny Bridge, which is the green bridge that crosses from behind the train station over to Whitcomb, is important. And what used to be Old Bridge here, a bit further downstream, is important. And then down here, we have Bristol. So it was always thus that the city was at the risk of flooding, probably since the early settlements. of course, and there's evidence for this of various sources. There's all sorts of sources. There's newspaper clippings. There's paintings. There's, of course, in more modern times, there's photography as well. And of course, we have also actually monitored the flow in the river. So people have been out there measuring the level, how high the water raises up. So we have long-term records, but they're not quite long, even though they're actually reasonably long on this river. So it's a big and it's an important river. They're just not really long enough to have a real understanding of the current flood risk. And that's why we try to extend it further back in time by trying to reconstruct some of the older events that hasn't been captured on modern equipment. But we know that happened because we've got evidence like this. So this is underneath Halfpenny Bridge. So this is the green bridge. We are on the Whitcomb side. Bath Spa train station is just on the other side here. Here's Joanna. She's pointing at some flood marks that's been chiseled into the concrete underneath that bridge. If you look closely, you can see the dates 1875, 1867, etc., etc. So there's some physical evidence, even though nobody ever measured the flow, because this predates the time when that was possible. There's some evidence that something big happened, and it's big. We know that because you can see here that Joanna is pointing upwards, and everybody's having to look up. So we're talking. That's the path. There's probably about another meter down to the river there, and then another few meters up here. And if you stand down there and you look at those flood marks, and you draw a horizontal line across, you can easily imagine the city center being underwater. So that's the sort of starting point. This is the kind of information we have tried to combine with our more modern mathematical and engineering tools. And I won't be talking about the mathematics of this at all. You'll be relieved to hear. Just to know that it is an attempt to try to combine history with modern technology, with the aim to try to improve our understanding of the risks. So before going into the historical floods, I thought maybe just say a little bit about where the water actually comes from, what causes floods on the River Avon. So here's a map. So down here we have Bath and Bristol. Up here we have Swindon, Harborough, Wells down here, Westbury. That black line you can see here, that's the boundary of the catchment area for the River Avon, which is this bit here. That's the catchment area for the River Avon in Bath. So what this means is that every time it rains, and every time it rain falls within this black line here, gravity will pull that, that water will land on the ground. Some of it will be sucked up by the soil, some will be stuck in trees. Some of it will end up on the ground and it'll be pulled by gravity into little streams, and those little streams will merge and form bigger streams. And eventually, those little streams will flow into the River Avon, and eventually the River Avon will make its way to Bath. So all the rain that falls up near Swindon is basically, we shouldn't worry too much if it rains in Bath, but if it rains in Swindon, that's causing us all the problems. There's a catchment area, so there's about 1,500 square kilometers of terrain upstream of Bath that's producing all the flow that you see. It's predominantly an area that's not built up. There's about 70% of the land use in that catchment that's what we would call urbanized, which by British standard isn't very much, and is unlikely to have a major impact on patterns we see in the river here in Bath. The river is simply too big that these small bits of towns and cities are not having a real effect. Mainly it's woodland, grassland, fields, etc. So this is an important river on a national scale as well. So the authorities, the Environment Agency and their predecessors have been monitoring the flow in the river for a long time. And this is the sort of observations you get when you monitor the flow in the River Avon. So down here on the x-axis here, we have time. So this is an example, 2014 December up to 2019 December. And up here on the y-axis, we have the magnitude of the flow. So this is the amount of water that comes per second in the river. So it's cubic meters per second. A cubic meter is a meter by meter by meter. So it's quite a lot of water coming per second through the city. And what you immediately notice is a very strong seasonal pattern here. So these periods here where we don't see very much, that's the summer. It's warm, the sun has dried out the soil, it doesn't rain very much, i.e. there's not very much flow in the river. Come autumn, it starts raining, the soil wets up, it gets filled up with water, it rains more, there's no space for it to go other than going in the river. So in autumn we see an upsurge in flow. And then these peaks correspond to sort of heavy downpours. Come March, April, it's getting warmer and it subsides again and we're back to summer and so it goes. So when we talk about flooding, when I talk about flooding here, what I really mean is periods where we have very high flow. It doesn't necessarily mean that anything was inundated or anybody was damaged. It just means period of very high flow. And for simplicity, we define that this way. So we take these sort of data here and we split them into years. And these blue lines is the boundary between years. Now, these are not calendar years. These years doesn't start on the 1st of January because that's in the middle of winter. So we would split, if we did that, we would split this wet period into two. And that doesn't seem reasonable. So we have a hydrological new year, which we celebrate on the 1st of October. And then that runs till the end of September, and then it's New Year again. And then there's another wet period. And what we do is we simply look through each year and we look for the highest observed flow value that occurred within that year. So that's called the annual maximum flow. Now, some years are wet, so there's that annual maximum peak flow is big. Some years it's not so wet, it's low. But if you look over a long enough record, you can see that this goes up and down, up and down, up and down, which is what makes this variation from year to year is what makes quantifying the risk of flooding very difficult. So what kind of data do we have to quantify risk? So again, here we have the River Avon coming up here up to Bathford, where it takes a turn and flows into the city. Here's Pulteney Bridge. There's the Bath train station, and then down to Bristol. Up here, I've drawn a little coordinate system where I have year on the x-axis here, and again the magnitude, the size of this annual peak flow. And the most modern observations we have of the flood magnitude comes from a very innocuous gauging station up here under the bridge where the train crosses over when you go to London on the train. Unless you know what you're looking for, probably won't see it. But that's been recording there for the last 50 years, since the very early 1970s. And this blue cluster is the size of the annual floods that has been recorded there. And you can see they are generally, the biggest one are around 300, but they're generally below 300 cubic meters per second. The 300 cubic meters per second is 300 tons of water per second flowing through the city. So it's a substantial amount. Before that was put in place, the Environment Agency's predecessor, the river authorities, put in a gauging station near St. James, so just on the upstream side of Pulteney Bridge, where they recorded flow from just before the onset of the Second World War up to the late 60s, at which pace they moved it out here. That's what they recorded. The red dots here is what they recorded at that point. And you can see there's sort of a bit more variability here. There's some big floods. That's the 1960 flood. We'll get back to that. That's the 1968 flood, the second biggest flood there. Well-known, substantial events. Before that, we don't really know. That's where people started actually systematically monitoring. Before that, we have no direct evidence. All we have is these flood marks and stories people tell, and pictures, like the ones that Joanna are pointing to here. So what we're trying to do is trying to see, can we convert the information contained in these water levels using our engineering river models to turn those into some equivalent values here so we can get a more complete record, so we can see how flooding has changed over the centuries. And we do know things happened and that it was bad. So here's some pictures that we found. You probably maybe have seen those from Bath in time. This excellent resource here. So there were floods in, this is the earliest one. We have pictures here, 1882, that definitely were floods prior to that. We know that, 1823 as well, even prior to that, but we then back in the time, but we don't really have much evidence. But here we go, that's Old Bridge. That's just a bit further down than the train station, a bit further down towards Bristol. And you can see that's probably some Sunday afternoon. People out there admiring the floodwaters gushing under this beautiful old bridge here. I doubt that would be allowed today. No. So you think, oh, that's extraordinary, but actually it's not extraordinary at all, because 12 years later they're out there again, looking at the same sort of phenomenon. So we know that something happened, or we know that it was substantial. It goes on like this again, 1947. Cities underwater. I think this is Lower Bristol Road. This is where the Bureau Happold consulting engineer, I think they have their offices here. See, that's inundated. And then, of course, the biggest event on record so far is the 1960s event. So just to put into perspective, 1960, so here's a picture. The problem with using pictures and water is that you don't actually know when this picture was taken. I don't actually know if this was at the peak, if this is the absolute highest it ever was. I have no idea because I don't have the time on it. But that flood was about 367, estimated to be 367 cubic meters per second. I say estimated because the instrument blew out way before that. The more modern equivalent was the year 2000, where we had 272, so almost 100 cubic meters less than that. And then Paul kindly forwarded me a picture from February 2020, where there was some flooding, and you can see we're way down. We're way down on the flux through there. So these were really sort of substantial events. So just to say something about the 1960s event, we called it a catalyst event because before this flood, the way the city managed flooding was to pay off the victims, or give charity to people who had been flooded, or compensate them for their losses. And then they would commission people to do studies on how to prevent future flooding, and then they would figure out that that's actually quite expensive. So we'll just keep paying people. Until 1960, at which point I guess the times have changed, and this was no longer feasible. So that's why we call this a catalyst event. Something really changed here. And this is the hydrograph. This is the water level that was recorded by the instruments behind the bridge. You can see there the rising limb. The water level is going up. So this is time down here, and this is the level in the water. And at some point, the instrument topped out, and somebody has kindly drawn on the original drawing, saying it probably looked a bit like this. So just in terms of volumes, we're talking about 110 million cubic meters of water that came over I think it's 2 days this event lasted. Again, cubic meters a ton, it's a metric ton, so it's a lot of water. And I've worked out, because we have an Olympic swimming pool at the university, and I asked him how big it was. So that's about 45,000 Olympic swimming pools that would have come through the city centre in those 2 days. So no wonder things were looking wet. I say this has all happened before. There was nothing new in that. Big floods in 1823. The city commissioned Thomas Kjeldsen, a famous engineer. He suggested taking out some bridges, making the river wider. They said no, it's expensive. 1882, they asked some other people who said build a bypass channel from Dundas Aqueduct down to Twerson, drill a tunnel. under Coombe Down. It's also expensive. I can't remember what Mr. Remington suggested, but all of these people, all of these suggestions are here. So construct a bypass channel. So this is the blowing a tunnel, or maybe using one of the two tunnels, I don't know, but a tunnel under Coombe Down. So that you just, when the flood comes, you just divert it outside the city. Other suggestion was construct a large storage reservoir dam before Bath to try to catch the water. Maybe we could construct some walls inside the city so that the water, when it comes, it just never floods the city. Or maybe we could just increase the capacity of the river to carry floodwaters. Maybe we just dig it a bit deeper, dredge it, take out some old bridges and send the water to the next community downstream and let them deal with it. And you can guess which one of these four options were chosen. It was number 4. And that's why the river and its environment looks the way it does today. It really is because number 4 was chosen, and it was an attempt to try to combat this flood risk. So I think one of the best professional days of my life was when Joanna and I visited the Environment Agency's archives down in Bridgewater. And in what was supposed to be an archive, but it was really just a storage room, we found all sorts of old drawings that related to what's called the Bath Flood Protection Scheme. So this was the initiative that was initiated after the 1960 flood to combat flooding. So we found a whole treasure trove of old engineering drawings from the 1930s and 50s, plans for how this flood protection scheme would be implemented. And all of this allowed us to construct a mathematical model of the river as it was before the changes you see today. So this was an impressive, really quite a big drawing here where they set out some phases of what they wanted to do. And the first thing they wanted to do, and probably the most important thing they've done, is to replace Old Bridge. This is this beautiful 5-arch bridge that all these people were standing on. You saw at the old floods. So get rid of that. They also wanted to replace some of the weirs down at Troyton Weirs, down by the little supermarket. Remodel Pulteney Weir as well, so that beautiful horseshoe-shaped thing you see now was implemented as part of this scheme. But really, the sticking point here is the Old Bridge. So Old Bridge, on Paul's slideshow before, you might have seen it. This was the bridge. This is the bridge that it exists to. It's not called Old Bridge anymore. It doesn't look like this anymore. But this is the bridge behind the train station, behind the bus station, if you cross over the river to the other side. Today, it's just as it looks like a concrete slab. But there's always been a bridge here. So we found evidence from maps in sort of 1694. Somebody published a map of a 5-arch bridge, St. Lawrence Bridge, over the River Avon down there. Here's another beautiful drawing of a 5-arch bridge in that location from 1819. And sadly, it came to an end in 1964 when it was found that this was the culprit in causing flooding in the city. So this is what it used to look like, 5-arch bridge. This is what it looks like today. This is the engineering drawing that we dug out from that. This is the modern engineering drawing. It's somewhat more symmetrical, but also much more efficient at conveying water at great speed out of the city. As such. So this is what effect did this have? So in order to figure this out, Joanna and I set up these engineering models, and we tried to implement different bridge structures. So this is Old Bridge. This is our attempt at putting Old Bridge in. So you can see the bottom of the river here, the riverbed, and you can see the water level here. This corresponds to the 1 in 100-year flood. So this is a big old flood we've thrown at the bridge here. And we've done the same for the modern concrete slab Churchill Bridge here. And what we measured is the difference in water level before and after the bridge during this big flood. And don't pay too much attention to this graph. The only thing that's really important is that here we have a graph that shows the water level during a flood event before the bridge. So that's the black line, and after the bridge, that's the gray line. And what you notice is that they're different. And at the peak, they're about somewhere between 0.5 meter and 75 centimeter, just short of a meter, perhaps, difference. So, which means, and here there's no difference. So it means that here there's no difference in water level before and after the bridge, which is hardly surprising because it doesn't interact with it at all. The 5 Arch Bridge does very much so. So this means that it effectively works like a reservoir, a dam during a flood event. It did. It doesn't exist anymore. It would have caused the water level to be upwards of 1 meter, 0.5 meter to 1 meter higher during a severe flood event on the city side of the bridge during an event. And that's, of course, why we see when you're standing down by under the halfpenny bridge and look up, oh gosh, they are tall. Well, yes, they are, because this bridge would have dropped it. And what often happened was that the bridge got overpowered, upstream. When you have a big flood, you get all sorts of things washing into the river as well. Timber yards got overpowered, trees, livestock. And there's lots of anecdotal evidence of trees and things getting stuck on the arches here. And once they get stuck, more get stuck, and suddenly you have yourself a dam. So this is probably even the best case story here. So while it's sad that we have to remove a 5-arch bridge, it's probably good for the well-being of the city centre. So this is the outcome of our research. This is as far as we got with our project here, where we have again these different sources of data and try to combine them. You can see these are all the historical events. I think we had about 15 in the end. They're sort of self-selected because nobody ever remembers a small flood. Why would they? So it's only, there's sort of a threshold here where we're only thinking about the big floods. Also, rather than giving it a point value, we've given it a range. We did a lot of thinking went into this, but it's given us a range to try to communicate that we think it's in this order of magnitude. And based on the evidence that we have, and that evidence might be biased and not entirely true, or maybe it's not complete. So there's a lot of sort of uncertainty in trying to pinpoint what exactly the flow value was. I mean, there's a lot of uncertainty in these values. These are probably an order of magnitude bigger. What we can say, though, is that there were some big events. There were some really big events, both prior to the Second World War, also in the period between the end of the Second World War and early 70s, and that we haven't seen anything of that order of magnitude over the last 50 years. So at this point where we change from red to blue points, that's the point where the Bath flood protection scheme would have been implemented. Now, these values here represent the amount. These values represent the amount of water that's coming off the hills near Swindon into the river. So they really should be unaffected by the Bath flood protection scheme. This has nothing to. They're not affected by it. This is what the scheme had to defend against. So it was built to defend against the magnitude of the 1960-1982 event. It's in that order of magnitude up there. It was built to defend. So you can claim success because we haven't flooded badly since, but also we haven't seen anything like that since. So my thesis is that it's untested. Lots of work went in, and it looks safe, but it's untested. We haven't actually seen the sort of conditions it was built for. So what does the future look like? This is, of course, where things becomes really, if it's difficult to know about the past, this becomes even more difficult and more nebulous. I think just to set the scene, I guess you've always seen this. This is the carbon dioxide concentrations in the atmosphere over the last million years. What stands out, of course, is sort of recent century. So we've really gone to town on releasing carbon dioxide into the atmosphere and the well-known consequences for climate change. So before talking about the River Avon, I just wanted to zoom out a bit and say this is some work we were involved in on a grand European scale, where we tried to work with people from all European nations and tried to collect flood data like the ones you've seen from everywhere, to try to see if there were consistent patterns of change on a macro scale across the whole continent here. And we came up with these two rather nice maps, I think. So on the left, the colors here are indicative of change in the sort of average day of the year when a flood occurs. So at what time of year does this annual maximum peak normally occur? And how much does that change? So if the map is blue, that means the flood season is pushed later in the season. So if it wasn't January, then it's now in February instead. That's what the blue means. The red means it occurs earlier. So we're getting an earlier season. So, but what's noticeable here is that these areas over here that are frost and snow dominated, we see that the flood starts to appear earlier as time in more recent times. There's an indication that snow melt is setting in faster. In the center of Europe, it's happening slightly later. And in the UK, we have quite a muddled picture where we're not entirely sure. I think it looks like bits are later, bits are earlier. I don't think we didn't come to any conclusions on that. On the right, that means change in the magnitude of floods. So that's the size of floods now. And there again, the picture is clear. There's less snow over in the east. The south gets drier, simply not as much water available in the south. But this sort of North Atlantic seafront here, where we're part of, becomes bigger. So this is a sort of macro picture that we are probably in an area where we're not entirely sure about the seasonality of flooding, when it happens, but we're certainly, the evidence is that things are getting bigger. And that has permeated into government advice on flood management. So if you study these things closely, the Department, DEFRA, the Department for Environment, Food and Rural Affairs, have issued these guidelines based on lots of people's research. Let's try to summarize it in an easy way to understand. So they've split the country into lots of little geographical units, and this is the unit we're in, the Avon, Bristol and North Somerset Stream Management Catchment Peak Flow unit. And what they do is they're looking at the size of the flood, the big floods. And we are talking about the 1 in 100 year flood, which is the key number that everybody uses to decide everything. There's the flood that is so big that you should see it on average once every 100 years. And what they suggest is that they have some epochs here, so the 2020s, so at the end of this decade, 2050s and 2080s. Of course, nobody really knows what the future looks like. So these are based on climate scenarios. So climate scientists tells us what's going to happen. And hydrologists have tried to convert that into what does that mean for peak flow. And so they have a range of scenarios. They have a central, a higher, and an upper scenario. And the numbers are not so frightening here at the end of the decade. 10% increase, 15 or 27. It's getting a bit big if you're looking at worst case scenarios. If you get to the 2080s, worst case scenario is a 71% increase in the magnitude of the peak flows. So that's the amount of water that the Environment Agency we could potentially see coming down our rivers here. What does that mean for flood levels? So that's really difficult to know what that means for anybody in particular. What we can say, if we do some back of the envelope engineering calculations, if we look at the end of the 2050s, worst scenario is 28% increase in flow. That would correspond to about a 25% increase in water level during high water flow alone. And if we look at the end of this century, we're looking at a 45% to 50% increase in water levels. So that's substantial. So just to give you an indication of what this would look like, I've tried to use our data here. So this is, again, here we have year. These are the 3 different data sources. Now I've got all our data points on. Done a statistical analysis of these data to try to work out how big is the 1 in 100 year flood today. If I'm just looking at this data that I have collected here. So the 1 in 100 year flood, you should expect to see on average once every 100 year. So we're looking back here at about 200 years, 200-year period, and we see that's the level. We see 3 observations, more or less, that are crossing this threshold. To me, that seems quite reasonable. There's a long wait here between the end of the 19th century and 1960. Really long waiting period there, and there's a really long waiting period here. But I don't know what's going to happen here. Can't forecast that, but it's not out of the realm. It's not out of the realm of imagination that this variability is continuing, and we just have been a bit lucky here. So if we take the worst case guidelines of the Environment Agency, that 100-year flood line will, by the end of the 2050s, have moved from here to here. So we should see on average 1 exceedance of this level up here. So we're now talking 550 odd cubic meters per second. So you would have to see some of these observations hopping up here. We would notice if that happened. That would be a really big flood. And by the end of the century, not only here, we would have to start to see floods that exceeds this level up here, which is getting close to 700, which is almost double of what we are seeing or have seen today. So if this is correct, and this is obviously, there's a lot of assumptions, there's a lot of uncertainty, and this is, I have to stress, this is worst case. We could be in for trouble in the future. So that was the story of that's as far as we got with trying to reconstruct the floods in Bath and give you a sense of what we're going to use them for to help make these risk assessments. We've recently been funded a follow-on project by the same funder, called the River Avon Trust. This time we've moved from the city of Bath, so we learned a lot of lessons from doing this. But we moved to outside Bath, to the Chew Valley. So down here we have the Chew Valley Lake. I guess up here with this coal tar soap, that's Bath, and Bristol is over here. And the focus of this project is flash floods. So what we've seen in Bath so far is not flash floods. Most of those take place in winter, when everything is wet and it rains a lot. Pensford, on the other hand, is a small village on the River Chew, and in the middle of summer 1968, there was a very dramatic event that destroyed road bridges and several houses in the village. And so that flood and that river is going to be the subject of our next project. And so this is must remember, this is the A37. Yes, it's the A37 got torn. The road bridge over the A37 in Pensford, you probably maybe recognize the viaduct down there, torn apart by this flood event. So there's a flood historian, of course there is. He's called David Archer, who's looked at flash floods across the West. And what he wrote about this flood was that there was some evidence that 175 millimeters of rain fell in Chewstoke down near the lake, and 125 millimeters in Bristol. Just to put that into context, in Bristol, in Bath, you would probably see about 800 millimeters over a year. That would be a normal year in this part of the world. So we are somewhere between 15 and 20% of all the rain in one year normal year falling within 2 days. Now, when that happens, things definitely happen, as you can see. That is the cause of flood. This is as we'll see in a second, this is the worst flood ever recorded on the River Tube. Interestingly enough, it's not the biggest flood that was recorded on the River Avon. It's the second or third biggest flood on the River Avon itself. So it's kind of a different kind of flood, which is why we're so interested in it, because it's obviously lots of communities living along smaller rivers all over the southwest who might be at a similar risk. Just to give you a sense of it, this is the kind of structure that measures flow in a river. So basically, you know the geometry, you measure the water level, and through hydraulic engineering calculations, you can convert that from a water level into a flow. And actually, it's a very well-monitored river, the River Tube. It's been monitored since the mid-50s. And these are the annual maximum peak flows again. And what you notice here is that all the gray years here is where the largest flow occurred in the winter season. The red ones is when it occurred in the summer. And of course, there's one standout flood here. And these are the official data. This is the sort of data that engineers and planners use to decide what is the flood risk and what can be built in these areas. So this data is really quite important for decision making and for flood management. And a flood like this would have a huge impact on those calculations. They're quite sensitive to these outliers. So the magnitude of this is important. If you look at the archives, the databases, it turns out that they think it was exactly 100 cubic meters per second, which is a nice and round number, easy to remember, but probably way off. And you don't have to look far in engineering reports before you find estimates varying from 250 down to 100. So what we know is that there was a big event. It was bigger than anything recorded before or since, but we have no idea how big it is. So this is what we're going to, Joanna and I will be looking at over the next 2 years. But we do know, and thank you to the Pensford Local History Group for setting us on trail of this. We do know that it was probably not the only event. There's a trail of evidence that stuff has happened before. These are newspaper articles addressing this. So we will start by focusing on the 1968 flood, and we'll try to figure out how big that was, and then we'll go scouring for evidence that could help us to also reconstruct these events. I guess with a little luck, we might find somebody who was alive in 1947 to tell us about it. Probably pushing it in 1926, and I hope we don't find anybody here. So that was the end of my talk. So just to sort of sum up, say there's a long history and very interesting history of flooding on the River Avon. It's interesting from an engineering perspective. It's interesting to read about all the social issues surrounding it and the policy issues. It's interesting that people intervened in the sort of mid-60s to try to stop it. And we can claim success because we haven't seen a big flood since. But my take on this is we haven't actually seen a real test of it. Nature hasn't thrown a real test at us yet. I think we can count ourselves lucky because there was a big nationwide flood in 2007 where certainly Oxford flooded, the northeast flooded, but somehow the weather decided to stop before it got all down to the southwest. So I think we've had a lucky escape. And that's not to say we will have that forever. Of course, the future is unknown, and it's really difficult and I think dangerous to pretend that I know what's going to happen. But I think the evidence is, as far as it's that all the evidence I can see is pointing to larger floods will happen in the future. Don't know when, but my guess is that it will happen. And the final slide is, would you like to get involved? So we've called our effort here Doku Flood. And we've set up a Twitter account. We have an email account. And what we found is been incredibly valuable to talk to members of the community about these things, because actually lots of people are interested in this, and lots of people have evidence. They might have experienced some of these flood events. They might have pictures. They might have, I don't know, any kind of evidence, that they were happy and willing to share, which could help us. Because, for instance, here we have a water level down on a wall in Pensford. So that's where they think the 1968 flood to. But do we actually know that that's where the 1968 flood to? Is it just that maybe the builder wasn't tall enough? Maybe he could only get to there. Maybe there was a brick missing and it fitted in there. I don't know. There could be all sorts of reasons why this is correct or not correct. So the more evidence we have to corroborate where the flood levels were, the more reliable our flood models become, the more interesting our research comes. So if you have any information you want to share, would like to share or talk to us about, please feel free to contact us via this Twitter hashtag or the email account, and we'd be more than happy to talk to you. I think that was it. Thank you very much.
Right, thank you, Thomas. That was terrific. We've got time for questions. If you'd like to ask a question, I'll hand you the microphone. Do talk into the microphone, because people on Zoom need to hear you. So, actually, I've got one in the front row.
How exactly do the gates work down at Putney Weir? Because there's that enormous bit of metal on rugby ground. So at what stage is it lifted or not lifted?
That's a good question. I don't actually quite know the answer to that. I think what I do know is that all these installations around Putney Weir are there to stabilize. Are not there for flood control, really. I think they're mainly there to make sure that that the water, when it comes here, is not too fast, in order to protect the foundations of the Putney Weir. Because if you get fast flowing water, you have a risk of developing scours. I mean, the sand or the ground in front of the river, the pillars there, starts to disappear. That's what happens. And that will weaken the bridge. So it's there to try to prevent the water from running too fast to maintain the river.
Because I remember in 2000 flood, when it was huge, and someone said they didn't open the gate in time, and that's when Bradford on Avon flooded.
I wouldn't know, but I would very much doubt that weir would be responsible for the flooding in Bradford. I don't think that's possible.
Okay, another question.
After the flood alleviation scheme was implemented, Greenhow wrote a brochure which finished with a warning to the City Council that if they didn't, that they must finish the scheme upstream of Putney Bridge. Otherwise, when the next big flood comes, there'll be a problem. Of course, they've never done that. And you talked about the old Five Arch Bridge, but you haven't talked about Putney Bridge, which actually constrains the flow perhaps a bit less, but does have pillars in the middle of the river, and also gets actually quite frequently clogged up with debris coming down the river. So do you have any comments about Putney Bridge and its impact on some holding water up as it comes down?
No, not that's. I'm trying to think back now. Did we look at Putney Bridge? I don't think we went to the same effort as we did with Old Bridge on understanding the impact of it. I think from when we constructed a river model for the whole, from probably upstream of up near Grosvenor Bridge and all the way through, and I think we did some sensitivity analysis, and it became quite clear to us quite quickly that there's that bend down by where this Old Bridge was. That's the real cork. That's the bottleneck that needed to be widened out. So I'm afraid I can't say more about it really than that.
Presumably, sorry. Yeah, sorry. Presumably now with the Old Bridge having gone as a bottleneck, does that mean possibly Courtney Bridge has now become the bottleneck, and it hasn't been tested? That is of course entirely possible. I think it hasn't happened yet. So I guess, well, I don't think anybody really knows is what I'm trying to say.
I'm interested in your pictures, the blue area, the red area.
Yeah.
It looked like there's been less flow since that period. Could that be, well, is that related to rainfall, or have there been other things gone upstream which have also been gone to make a difference involved?
That's a good question. So, to my knowledge, there hasn't been much going on upstream. I mean, obviously, Chippenham would have grown. Some of the smaller villages would have grown, but I think they're not big enough. Given the scale of the whole catchment, they're not big enough to see that. We haven't really seen much trend. If you're looking at long-term trends in rainfall, it's very, very difficult to pick out whether that's happening or not. So the answer is I'm not entirely sure why we see less variability, whether it's some systematic factor or whether it's chance. And when you look at a cloud of point like that, it's quite often tempting to look for patterns in them, because that's what you do as a human being. But when you start looking at the probability of actually these things popping up, it's not as unlikely as it might visually seem. So yeah, what I'm saying is that the variability seems bigger, but it's not necessarily as significant. It might not necessarily be so. It's just that it happens to have happened this way. I don't know if that's a very good answer to it.
Thanks, Thomas. I'm just wondering if you took some of those historic floods and you put them through the existing state of the river at the moment, did you ever look at what the inundation levels would look like and how they would handle some of those big floods that have happened historically?
Good question. They should be able to accommodate them, because that's what the scheme was designed for. So when they designed the scheme, they looked at the biggest flow on record, which was 1882, I think. So that's what it's designed for. Of course, this was designed 60 years ago, before the advent of modern computers and so forth. Nonetheless, so we should be okay. We should not see dramatic flooding of the city centre at those stages. I think it's when we get beyond that, when the next record breaker comes along, then I think we're in uncharted territory.
Andrew, I think you've got a question too.
You mentioned that I remember you mentioned about dredging. Now, presumably dredging done, and has river management, so it's been dredging now, because that would help increase the depth of the water.
I don't, but I don't know if the environment. I doubt they do dredge it anymore. I think they dug out the sediment. They did it, yeah. And you can see metal. You can see this metal sheeting along the riverbanks if you walk along, which was also put in try to stabilize the riverbanks and keep the geometry smooth, because that just means the water moves faster without the less resistance you have. So if you have very smooth channels, you don't get as high water levels. So that's why the metal sheeting is in there as well.
Okay, we've got quite a few questions online, which I'm going to field. One is from Anna. What engineering or other interventions might we see in the future to mitigate the impact of flooding?
That's a good question. It's also a very difficult question, especially so when you have a city like Bath. I mean, the obvious question is, get out of the way, because these things are happening. But we've already built the city, so they can't really get out of the way. So we're going to have to do something else. The traditional engineering approach would have been to put concrete and try to defend our way out of it. The more modern approach is a more, I would say, ecological approach, where people are looking at, well, where does all this water actually come from? Well, it comes from all these fields that are upstream of the river. There's 1,500 square kilometers of land upstream of us. That's really where it all comes from. It doesn't really matter so much what we do in the city, because the water's coming from up there. So we should probably try to stop it or manage it up there somehow. And what's being promoted is what we would call nature-based solutions or natural flood risk management. So this is where people are attempting to, introduce beavers, for instance, to build natural dams. Or maybe you construct something that looks like a beaver's dam. You try to cultivate the land more sensitively so that when it rains, it's not so, the agricultural land isn't so compacted, so the soil can absorb more of it and hold on to it and release it slower afterwards. You might try to plant more forest, more trees, in the hope that the leaves will catch some of all this water, and maybe the trees will drink some of the water so that the soil isn't so wet. And there are lots and lots of initiatives like this going on. And I think the jury is still out on whether this works. I mean, it obviously works for several reasons. Trees are good. It's nice to plant. They have lots of benefits. Biodiversity. It's nice to walk in the woods and so. How effective they actually are in combating should the 1 in 100 year rainfall event occur, whether it matters if we have 1 or 2 more trees, is probably not. I would have thought, but that's the philosophy. Let's move the vulnerable areas, Bath. Let's move up and prevent it before it happens. So I guess one of the ideas they had in the 19th century was to build a big reservoir upstream. Now, I don't think anybody's ever going to build a big reservoir upstream on the River Avon. But people could have floated ideas like there's land that is perhaps less valuable than the center of Bath. So if a really big flood comes along, maybe the city could compensate some of the farmers upstream and say, let their land flood, and you store it on their fields. And it might ruin their crop, and you have to compensate them perhaps. But at least you protect the center of the city. So I think that's moving away from this sort of engineering-based approach where you do some calculations and then you put in concrete to protect it. Honestly, it wouldn't really work in Bath, would it? I mean, one of the ideas they had was to build levees inside the city. You could just imagine the outrage if we did that today. Built a flood wall along the river so you couldn't walk along and see it. Because, I mean, it happens on average once every 100 years. It means there's 99.999 other years where you actually would like to walk along the river and see it. So I think it has to be done quite sensitively.
Okay, there's another question online. Does significant other places upstream or downstream have greater vulnerability of flooding?
That's a good question. I don't think it. I will start by saying I'm not 100% sure. I haven't done those calculations, but I would say logically it wouldn't. I don't think it would matter upstream. They deal with the water that comes upstream of them. Once it passed Chippenham or whoever lives there. It's out of sight, out of mind. Whether it matters to the people downstream of us, that's probably a different matter. And I guess, and I don't know, but maybe people who have lived in Keynsham or Salford for a long time would have a sense of whether they see flooding more frequently, because managing floods is severe. You're moving around the water. You have this one amount of water, you have to move it around, you have to put it somewhere. We've chosen not to put it in Bath. We've chosen not to store it upstream. Well, then it have to be stored downstream. And that's where, Keynsham and Salford. So I would say, probably, if you did the calculations very carefully, you would find that those communities are probably at slightly higher risk. Then you get towards Bristol, but then I think it becomes even more complicated because you've got the Bristol Channel, which is highly tidal. I think they're probably more at risk from the storm surges coming up the Bristol Channel rather than River Avon itself. So I think it's that stretch between Newbridge here and where the river becomes tidal down in Bristol. That's most at risk from us having let go of it.
Okay, one more question online. Can you say anything about floodless near Grosvenor Bridge? I think this looks like near Grosvenor Bridge. Yeah.
I live near Grosvenor Bridge. No, not in any great detail. It's up where actually not much have changed up there when you look over history. And so the Bath flood protection scheme did nothing up there. The channel is remarkably geologically stable, so it wouldn't have changed much over time. So I can't tell you exactly what the risk is, and it depends what you mean by risk. But my guess is that it hasn't changed very much, other than if it has changed if the climate has changed. So if the climate has made it more risky, then yes. If the climate has made floods more frequent and bigger, then you would have seen that up there as well.
Probably Weir was rebuilt in the 1970s. How much does its horseshoe design relate to aesthetics or to functionality, or a combination of both?
I think it's an aesthetic. It's purely an aesthetic, a very effective one at that as well. I think it's quite a beautiful. I mean, there was a Weir before that. I think Paul had one of his pictures circling around. It's just a straight bit of concrete across the river, again to try to manage the velocities of the water to prevent scouring of the bridge, to preserve the bridge. So it is I think, the answer is aesthetic. It's an aesthetic feature.
Okay, have we got any more questions online? Andreas, or? Oh, no. Okay. I got one more. Yes.
We're restoring the Wilson Bath Canal, which goes through places like Nottingham and Kidman. At the head of the catchment, we're crying out for water, we're told we can't have it. We're trying for a change of attitude. I'm not going to be shovel-ready for 11 years now.
So is that
The Knoxfield link has been shovel-ready for 11 years. We still can't get permission. It's the time for a change of attitude.
So I'm unaware what the question relates to. Sorry.
Well, we are crying out for water to use in the Wilton Bath Canal, and they're told we can't have it.
Oh, I see what you mean.
You've got too much water. So should we not be talking to us?
I see. Yes, I think one thing I need to qualify that I am not making any of these decisions at all. I am sitting in my ivory tower looking at it. So it's so yeah. I'm in favor. I wouldn't have known why they've done that for ecological reasons. I suspect that I don't know the answer to that, I'm afraid.
Okay, well, if there's no more questions, I think.
Good evening. Has anybody looked again at the bypass tunnel concept? Is that practical too? Because the tunnel exists.
Yeah. Yes.
Would it be adequate for the flow?
It's a good question, and I was very. I think the answer is no. I don't think anybody has. It's a very intriguing scheme. I think it's from, is it called Dundas Aqueduct? I think that's where it was supposed to come out, and then you're sort of looking at a map, and it's an incredible feat if it has to go through, and then it goes up to Twerton and down by where the weirs are, down by Little. We did try to get hold of the original report that proposed this, but this was COVID. We did this during lockdown, and there was just no way of getting the report, and then unfortunately the project ended. But actually, this reminds me that it would be actually really interesting to find that report, to find out what exactly was proposed, and I doubt anybody would enact it now, but it'd be an interesting project.
Okay, I think that's probably the last question. So thank you very much, Thomas. It's been very interesting. It's interesting that you actually sort of take two disciplines, history and civil engineering and technology, and it's great to see those things happening, as well as looking at the past and seeing how it can influence and help us in the present. So thanks again. Thanks everybody for coming.